class, we are now on chapter 21.4 and 21.5. I joined 21.5 because it's a really short chapter. So I didn't want to have it by itself for maybe 2 minutes or so. All right, so nuclear stability. Why are some isotopes radioactive and others are stable? So that's what we're going to look at here. Look in this section as to why some of them are stable, some of them are radioactive, and when they are radioactive, what causes them to emit certain radiation over others. And the answer lies pretty much in the ratio of neutrons to protons in the nucleus. So the protons in the atomic nucleus are all positively charged, and they have an electrostatic forces between the protons which repel them away because they're all positively charged. However, the nucleus does not fly apart. This is due to a force known as the strong nuclear force, or just in your book it's called the strong force. And that keeps the protons together. This pulls the protons together, overcoming that electrostatic repulsion. This strong nuclear force is an attractive force, and that all the nucleons, and nucleons are protons and neutrons, exert on the nucleons. So I think I just repeated a word. Force all the nucleons exert on other nucleons, excuse me. Didn't sound right when I was saying it. Okay, so the addition of neutrons to a nucleus adds a strong nuclear force. And that keeps it stable. And it does that without adding electrostatic repulsion. So it provides an overall stability to the nucleus. However, there is a fine point that stops. So there's a limit to how many neutrons you can add. Eventually, what you'll do is you'll add so many that it will start decreasing the stability of the nucleus. And why is this? This is because of energy levels, which are similar to the way we understand it with electrons. So there's the energy levels for the nucleons that are in the nucleus. The addition of too many neutrons puts the excess neutrons into higher energy levels, which destabilizes the nucleus. Remember, chemistry is all about lower energy, makes the most stable. So now that we're adding neutrons into higher energy levels, that's not happening. It's causing this to become destabilized. So there is now a struggle. This leads to a struggle between the attractive and repulsive forces in the nucleus of the atom. So if these forces end up being balanced, then that means that the nucleus is stable. But if they're not balanced, then this causes this nucleus to be unbalanced, and it's going to release this excess energy as radioactive decay. So 80 out of the 118 elements in the periodic table have at least one stable isotope. We have 253 stable isotopes that have never shown to decay, and more than 3,000 radioactive isotopes. The majority of isotopes have an even number of both protons and neutrons, and nearly all the rest have an even number of at least one nucleon. And 5 of the 253 stable isotopes have an odd number of both protons and neutrons. Why is this a big deal? Because we have to look at in addition to the ratio of neutrons to protons in the nucleus, another factor is the actual number of protons and neutrons in the nucleus. So we look at a ratio, but we're also actually looking at the actual number that exists. This plays a role in the stability of the isotope. Remember, this also adds up to the mass of these isotopes. So the majority of the stable isotopes have even number of both protons and neutrons. And I think I have it on this page. Yeah. So you can see that this shows you how many isotopes, excuse me, have an even number. And then it starts breaking it down where it's even odd, odd even, and then odd and odd. Okay, so now we're going to look at a ratio. The ratio of neutrons to protons. Remember, N is neutrons versus Z is protons. If the neutron ratio, if the N over the neutrons over proton ratio is too high, neutrons are converted to protons via beta decay. If the neutrons over protons is too low, protons are converted to neutrons via positron emission or electron capture, or alpha decay, though it's not really as efficient. So what does this mean? Well, we can look if the total number of nucleon number adds to a magic number. So we in your book, it talks about this magic number. So what they have found that certain number of protons and neutrons make more likely that nucleus will be stable. So nuclei with the numbers 2, 8, 20, 28, 50, or 82 protons, or 2, 8, 20, 28, 50, 82, or 126 neutrons tend to be more stable than the isotopes that do not have these numbers. That's what they refer to as these magic numbers, because they are they have a special stability tends to be with these numbers. And these numbers also support a model in which atomic nuclei have energy levels that match the way we understand it with electron energy levels of an atom as well. Okay, so we're going to look at the Delta stability. Now, what the Delta stability is, and there's a graph in your book, and I pulled one from another book as well. I think both together will help you understand this. It's also called the valley of stability. If you take all the stable nuclei and you plot N, which is the number of neutrons versus Z, the number of protons, we get a graph that looks like this. And that's what this first slide is talking about here, about where it is on the graph. You can actually determine if it's going to have beta decay or positron emission or electron capture. And that's why I put two different graphs, because you can see one says too many neutrons, one says too many protons. And where those dots are in the middle, that's the Delta stability. So what this is that if you look at a graph, it shows the relationship between the neutron and proton ratio and stability. And I can go back and forth if it makes it easier to take a look at this one with colors, and kind of points out other things where this one points out other things. So I put them both. So the points that are present in the stable nuclei, that's the points that we see are the stable nuclei. These dots or points. These are the locations based on its number of neutron and protons. This is called the valley of stability. So what you need to look at is you see the atomic number Z. So it starts at 0 and it goes all the way to 120. These are the atomic number, protons. And then we have the number of neutrons. So as we start looking at an atomic number, then we can match it to the number of neutrons. And one over the other is going to give you this 3 significant figure number. And based on that, you can see where it's N, when this is just 1 to 1, we can start seeing if it's here, if it's below, if it's above, or if it's actually in this valley of stability. And this one's colored, so it actually tells you what's happening if it's got too many neutrons, if it's got too many protons. And that's what this page is telling you. If it's too high for one, then it's going to be beta decay. If that number is too low, so it's in the graph but the valley below, then it's going to cause something else. So that's what this means. If it's above, if it's below. Excuse me. Okay, so another way to tell isotopes, and I have some problems to show you this, is you can also look at the mass number. The mass number, remember, isotopes tend to have a different mass than the mass that's on the periodic table. The periodic table is an average atomic mass. So if it's above that or below it, you can also get an idea of what's going on by comparing the isotope that you're looking at with the average atomic mass number, which tends to be the most abundant isotope and the most stable from the periodic table. Okay, so low atomic masses, the most stable nuclei tend to have equal numbers of protons and neutrons. So that's what we're talking about, low masses on the periodic table. But as the numbers increase from there, however, the atomic mass on the periodic table becomes increasingly greater than the atomic number. Remember, the mass is made up of protons and neutrons. So if you have the protons and you double that and you still haven't met the mass, then that means that you're starting to get more and more neutrons in to make up this mass. This indicates there are more and then as we start going up, we see this number, the numbers increase, the atomic mass number increase. This indicates that as there are more protons in the nucleus, you need more neutrons to balance those forces and stable that nucleus. Lead, which is Z equals 82, is the element with the highest atomic number that has a stable isotope. Okay, so then this is interesting, is that atoms that are above Z, a proton number of 83, are radioactive. In nature, often one radioactive nuclei changes into another, and they will keep changing. They will change until they get to a stable nuclide. That's what this decay series means. So if you see when arrow that goes this way, it's alpha decay. If it goes this way, it's beta decay. So you see this will keep changing into from the parent nuclei to a daughter nuclei, and it will keep going until it gets into a stable nuclei is reached. So we'll go through all these steps. Typically, nucleides decay in a manner that brings the daughter isotope closer to the Delta stability than the parent was. So that's what this is. This is a decay series showing how it will keep changing until it gets to something that's stable. So predicting decay mode. Compare the mass number of the isotope to the atomic mass of the element to determine if the nuclei lies above or below the belt stability. I have problems that we're going to look at that will do exactly this. We're going to look at the mass number and compare them. Heavier nuclides typically decay by alpha decay, an effective way to reduce the atomic number. Neutron-rich nuclides above the belt of stability tend to decay by beta decay, which I've already stated. And what it does is convert a neutron to a proton, and it moves the nuclide down and to the right. So you can see that if you look at this, this is also, as it going down, it's changing the number of neutrons, and it's also changing the number of protons. So remember, we changed this into an entirely different atom. Proton-rich nuclides below the belt of stability tend to decay by positron emission or electron capture, because converting a proton to a neutron moves the nuclide up and to the left. I know this is a lot of new information, so take your time in trying to understand. That's why I'm showing you two different graphs as well. So predict the mode of decay for each of the following unstable isotopes. And what we're going to do is look at the mass, the average mass in the periodic table. Okay, I'm just going to show these to you, and then I'm going to go over each one to help you understand what it is that you need to look for on here. Okay, so the first thing we look at, we don't have any isotopes that have a proton atomic number over 83. So there is no alpha decay that's happening here. Now we're going to check the mass number of this isotope to the element's atomic number. So for the first one, we're going to look at phosphorus. The average atomic mass of phosphorus is 30.974 on the periodic table. We have a phosphorus 32, so we are comparing these. This means that the mass for this phosphorus is greater than the atomic mass. And because that it's heavier, that means it's above the belt of stability. So it is, if we go up here, it is above the belt of stability. And let's go back here. Okay. Excuse me. So because it's above the belt of stability, it's going to decay by converting a neutron to a proton via beta decay. The daughter isotope is stable, which is sulfur 32, which has a mass very close to the average atomic mass of sulfur for 32.07. So that it gets it to a stable element. Now the second one, we're looking at carbon. The average atomic mass of carbon is 12.011. Carbon 11 is lighter than that, so it is below the belt of stability. So let's go back up. It's below the belt of stability. All right, so here we go. And because it's below the belt of stability, it's going to decay by converting a proton to a neutron via positron decay. The daughter isotope is stable boron 11, which has a mass very close to the average atomic mass for boron of 10.811. Now C, the average atomic mass of oxygen is 15.999. Oxygen 15 is lighter than that, so it is below the belt of stability and will decay by converting a proton, to a proton, converting a proton to a neutron, sorry, even I can get confused on this, via positron emission. The daughter isotope is nitrogen 15, which has a mass about 1 mass unit higher than the average mass for nitrogen of 14.007. Nitrogen 15 is stable, but it makes up only about 0.4% naturally occurring. That's not one I would ask. It's a little tricky. I would try to avoid something like that. D, we are looking at hydrogen. Now we know that the average atomic mass of hydrogen is 1.008. We're looking at 3. This is called, I never say this right, tritium, Tritium. It's heavier than that. So it's above the belt of stability and will decay by converting a neutron to a proton via beta decay. The daughter isotope is helium-3, which has a mass 1 mass unit lower than helium, which is 4. But helium-3 is stable, but it's only on trace amounts in Earth. So those weird ones like that, I'm not sure I would ask you something like that because that's really something difficult. All right, a nuclide has a mass of 116. The atomic mass of the element listed in the periodic table is 102. Will the element undergo beta decay or positron emission? positron emission. This is above, so it's going to go above the valley of stability. It's going to be beta decay. A number of factors contribute to whether a nuclide is stable. Among them are the ratio of neutrons to protons, the number of each nucleon, and whether the number of protons and neutrons are even or odd. Based on the ratio of neutrons to protons, a graph can be drawn in which the stable isotopes form a rough line, that's that valley, and surrounded above and below are the unstable ones. Radioactive nuclei tend to decay in a manner that will bring them closer to a stable configuration of neutrons and protons, and it will keep doing that until it gets to something that's stable. All right, so now we're going to do 12.5, and 12.5 is detecting radioactivity. It's like half one page, if that. Here is from another slide, and we basically covered more of this than 112 is. Radiation levels, if you guys remember Fukushima, that's the nuclear plant in Japan, and this happened in 2011. It's a disabled nuclear power plant, and it suffered a 9.0 magnitude earthquake and tsunami that suffered severe major damage. And through a chain of events that caused radiation leaks and permanently damaged several reactors. And as far as I know, I think that it's still leaking. I might be wrong on that. I haven't checked on this, but it really did do major damage and a lot of things going on. It's pretty bad. People, if you go on YouTube, I'm not saying to check this out, but there's a lot, you're not supposed to be in that area because of how the radiation is still so high. And everything's just left like a ghost town. And people still go in there abandoned. They'll sneak in and film all the stuff that's there. But you didn't hear that from me, and I'm not condoning it. Okay, so detecting radioactivity. Particles emitted by radioactive nuclei have a lot of energy and therefore can be readily detected. Thermoluminescent dosimeters. Now, this pretty much, the name tells you, if you understand breaking down these words, what it does. Thermo is heat, luminescent is light. It's a dosimeter. I have had to wear these when I was in a my physics lab. It's really small. You don't think it really would do anything, so you just put it on until you actually understand what it's supposed to do. It contains crystals of salts, and they are excited by ionizing radiation. So if there is radiation in the air, that will be ionized. Those crystals will get excited, they will heat up, and as the electrons relax to their ground state, it's going to emit light. So that's going to light up, and the amount of light is proportional to the radiation exposure. Luckily, mine did not light up. Detecting radioactivity, how does that happen? Well, we can also look at something that is a Geiger counter. Hopefully that's something you've heard of. And a Geiger counter is a common instrument that detects alpha particles, beta particles, and gamma rays. And what it does is it uses ions produced by radiation to create an electrical current. So if there's radiation, that ionizing radiation will pass through this argon-filled chamber, and that's what you're going to see, is it will actually ionize that argon gas. And when it does that, it will give brief tiny pulses, and that's what you hear are those clicks. And those clicks are, every click signals a particle is entering the detector. So every click of that is telling you something. These high energy particles from a radioactive sample cause the gas to be ionized, and then it can carry an electrical current for a short period of time. So that's what you're hearing with that. This is a very simplified one. What it is here it is. This is very similar to what I'm showing you here, but it breaks it down a little bit more. So it goes into, here's argon gas. It ionizes it. The positive ions are attracted to the negative wall. The ionized, the electrons here are attracted to a wire, and it generates a current supply. And that's what you'll end up hearing or seeing here on this. Okay, detecting radioactivity. Another one is, I know I'm not going to say this right, I tried to practice this. Scintillation counter. And this is also another one. It's referred to right here where it tells you that these can be used to detect and measure disintegrations. It's able to count the number of flashes per minute. Your book didn't really give anything on it, so I found this online, and I found this really interesting with what the crystal is, and when it is excited, what it actually looks like. So that's it's very interesting here. Compare this to that. And if you watch Thor or Marvel or any of those things, this kind of reminds me of Thor Ragnarok and any of those things. Anyways, that's a whole other conversation. All right, so this is an example from your book, and this actually goes with the last section, but for some reason I put it here. Predict whether each nuclide is more likely to beta decay or positron emission. So we have magnesium 28. We have 16 neutrons, 12 protons. This is 1.33. However, for Z equals 12, the stable nuclei should have about N over Z is about 1. You can see from the periodic table, the atomic mass of magnesium is 24.31. So this is heavier. This has a mass of 28. This is going to be too high, and that's going to undergo beta decay. So it's going to convert to a neutron, from a neutron to a proton. Magnesium 22 has 12 neutrons, 10 neutrons, and 12 protons, so it gives you a 0.83. What do those numbers mean? Well, there's two ways you can detect this. You can, let's go all the way back here. That's what these numbers are. You see where this valley is, and these numbers here, if it matches in here, so this is about 1, and if these numbers, this is about 1.27, you can add up what would be on the periodic table, and then you can use these numbers that tend to be above or below, and they give you an idea as well. But looking at atomic mass to me is easier because it gives you, you can very easily see if it's above or below. You can see from the periodic table that the atomic mass is 24.31 again. This has a mass number 22, so it's too light. It's below the valley of stability. That means it's going to go positron emission, and that will convert a proton to a neutron. Electron capture would accomplish the same thing, but positron emission is the only decay mode observed. And then the last one is molybdenum 102, which is 60 neutrons and 42 protons. It gives a number of 1.43. However, for Z equals 42, we see that the stable nuclei should have a ratio of 1.3. You can also see from the periodic table molybdenum is 95.94. So this is too heavy, and that is too high, that ratio. So this is going to undergo beta decay, a conversion of a neutron to a proton. A number of factors contribute to whether a nuclide is stable. Among them are the ratio of neutrons to protons, the number of each nucleon, and whether the numbers of protons and neutrons are even or odd. Based on the ratio of neutrons to protons, a graph can be drawn, which the stable isotopes from a rough line, and surrounded above or below, that's the valley of stability. I think atomic mass is also a kind of straightforward way to figure this out. Radioactive nuclei tend to decay in a manner that brings them closer to a stable configuration of neutrons and protons, and that's what that decay